All right, my name's Tom Erb. I'm a friend of Steve's, just kind of an old family friend. I do a lot of RC flying, and that's how I got to know the Eves family years ago, with Steve's younger brother, Brian. I've flown RC with him for over 20 years, and spent a lot of time with him, his family, Steve and his family, and his mom and dad over the years. But I'm from Alliance, Ohio, which is I'm about 5 miles east of Hartville, which is only about 15 miles from Steve's house. And Steve came to, we had a friendly family poker night, over at Brian's house, his younger brother's, one night. And Steve come in, and he'd come over every once in a while, and he'd come in with these pictures. He said, I think this is going to be my next big rocket project. And I'd worked with Steve some on some past projects. He'd built a shuttle with the 2 boosters, the fuel tank, the shuttle and everything. Probably, I don't know, 12, 15 years ago we built one. And we had a really good flight. We didn't get much altitude, but because of my RC experience and stuff, I was flying the shuttle. And we went out in a big field out in the middle of Hartville there and flew it. And it flew really well. I could steer the rocket on the way up, and we just couldn't get a lot of altitude because they didn't have the motors developed like they have today. So, I'd worked with Steve in the past on projects like this. But we actually took the shuttle later and strapped it to the back of one of Brian's airplanes and flew it piggyback off another big quarter-scale airplane, and we've flown it quite a bit. We had a lot of fun with it. And so anyway, he come and was talking about this project and got to thinking about it. I said, yeah, that'd be cool. And, let me know. And probably, I don't know, 4 or 5 months later, he came back to play poker with us one night. And he shows me pictures, and it was like, oh my God, you got to be kidding me. He really is doing this. And I knew all along that he'd be doing it, but he got started without me, but that's all right. He's a gung-ho kind of guy when he gets his mind set to something. And that's when it really started to take off. And over the next about 1.5 years, I paid a lot of different visits to the house, different times. He'd call me up, we'd talk and discuss different things. And as the project went on, we kept working on different sections at a time. As it developed itself, and it was just I was just in awe at what we ended up with, and even all the way through the project, thinking about all the different designs we did for some of the release mechanisms and everything else, and as the project got closer, I spent more and more time as I could over, just helping out wherever we needed to. So it was a lot of fun. Saturday mornings, a lot of times I go down to the hobby shop, hang out with my RC buddies. We go get lunch. And then for quite a few Saturdays, it was, we got to go to Steve's and see what we got to do this Saturday.
Well, I'm the guy that built this insane project behind me. I'm Steve Eves. We're going to fly the 36-foot tall Saturn V tomorrow.
What are we doing now?
We're going to pull the motors out of the trailer. We're going to prep the rocket, and we got a crane showing up that's going to put it on the tower. We're going to light it up with spotlights tonight and sit around and have a good old time.
Now, how long did it take you to put this together?
I got 2 years invested in the rocket itself.
And we're going to give you a quick overview on the construction processes used to build the Saturn V. It's built mostly out of aircraft grade plywood, 3/8 of an inch thick. The 2 bottom centering rings were actually 3/4 of an inch thick and of oak, and this is the first picture that we're showing here is the 2 bottom plates being cut with the motor holes and the slots for the fins. I used a router to cut most of these pieces. And next we're going on to showing the structure, the vertical stringers of the rocket. These are also made out of 3/8 inch thick aircraft grade plywood. It's a 7-ply wood that is extremely dense and extremely strong. The very bottom section of the rocket showing the motor tubes and the supporting structures. I did cut holes in a lot of the lower airframe pieces to try to cut the weight down on the back end of the rocket. Second layer of wood, and these are actually triangular shaped to try to transfer the loads from the motors back out to the outside of the airframe. The outside structure of the airframe is where all the strength was, and we needed to keep that force distributed back out to the airframe. And this structure here was designed to do that. As you can see in the following picture, the rabbet joints that were made between the vertical stringers and the horizontal, these were all cut in with a router and epoxied into place, as well as a layer of fiberglass cloth and resin. Actually, it was epoxy resin to stiffen the joint even more. This is early July 2007. Actually, wanted to get some idea of the size of this thing I was building. This was all segmented at this point, but we drug it out into the driveway and clamped the sections all together. And about 5 of us threw a rope over the top of the large tree I have in my front yard, and we actually stood it up for the first time. It was pretty surprising how all these pieces accumulated into such a very large piece. The piece you're looking at here is about 22 feet tall. And vertical, it takes on an entire new aura, which we experienced all the way through building this. Laying down was one thing, but once you stood it up, you began to realize how big the rocket really was. Starting to apply the skin, and if you'll notice, there's an inner layer of plywood on the inner part of the vertical stringers. This was to keep the stringers straight and keep them from bending under load when the motor's fired. The outer skin reinforced the outside edge very well, but the inner edge, I was afraid of it flexing, and you lose all your strength in those ribs when it flexes. So we glued a 1/8-inch plywood on the inside edges as well as the outside, and you basically achieve a series of boxes stacked on top of each other, which really contributed to the strength of the entire project. Wherever there was a seam between the segments, these were actually straddled with aluminum and bolted into each section. One of the problems in working with laminates is you're gluing to one layer of the laminate, and the strength of the laminate itself is subject to how much glue you can get on it. So by bolting in and going through all of these layers, it increased the rigidity of the structure markedly. Here of the upper section in its early stages, I found that at that point in time the garage wasn't long enough, and one end was almost touching the front wall and the rear end's hanging out the back door of the garage. So we ended up taking a wall out of the garage to complete the building process. You're looking at the retaining pins. One of the innovative features that I used on this rocket was I did not want one tube sliding down into the other tube. I was afraid with the 300+ pound weight of the upper section that aerodynamic forces on it may not allow it to slide out. So what we did is we basically sat one piece on top of another and used a locking mechanism, and these 8 aluminum pins sticking through the top ring are what was used to lock the upper section onto. Thereby, once these are unlocked, it's basically sitting on top of each other, and they would fall apart at minimum, but we ended up using an airbag to push them apart. But this way there's nothing to hang up should the forces on the rocket come from the side and stress that joint. Nothing to slide apart. It simply fell off the top of it. These pictures here are of the inner lower section. I was reinforcing the center tube area with a 40-inch diameter on the rocket, and all the motors within the central less than 2 feet of that. The stresses on the center of the rocket were incredible, and the strength on the outside of it is where I wanted the load to go to. So here you're looking at 4 oak ribs that run from the center of the rocket back out and into the airframe. That's also to help transfer the load to the outer part of the rocket. As you'll see in this picture, we're starting to attach the outer skin. The outer skin was a 3.7 millimeter Lewin plywood. It was 3-ply. I bought it in 3x7 sheets. Now each of these sheets was cut to fit size-wise for 2 segments of it. They were epoxied into place on each of the ribs. There's 16 ribs going around the rocket. Each one of these was epoxied down and then nailed with about 1.25 inch long headed brads. And the reason I did this was an air nailer would have recessed the heads into this plywood. Plywood was so thin that we couldn't afford to have these nails pulling through it. So every one of these nails was driven in by hand. This is another shot down in the lower end of the rocket. I was afraid of deflection of those triangular shaped braces. So I put a ring in there to keep the inner part of those triangular shaped braces from flexing. Just another added feature to try to take that load and distribute it into the airframe. It's another shot here of the skin being applied to it. Now you're looking at the bottom section. The skinning has now been completed, and we are prepping to apply the fiberglass. As you can see in this photo, the fiberglass is being applied. What we used was a 16-ounce woven roving fiberglass. It is a very coarse fiberglass, very strong. We laid that on in a circular motion, and then over top of that we laid 8-ounce glass to help ease the pains of filling the glass, as well as adding 2 layers of fiberglass to it. And we applied that in one session so that the fiberglass did not have a chance to cure. I wanted no bonding issues between the 2 layers. So it took me and another guy about 6 hours, and he's a professional fiberglass man, to lay the glass just on this section of the body. A picture of the finished product with the glass all on it and cured. At this point we added about probably 7 gallons of auto body filler and many hours of sanding to smooth up the surface, take the imperfections out, and ready it for primer. As you see here, different colors of hardener made a different color of filler, but this was what it looked like when we started applying primer to the outside of the rocket. Here we're going to take a quick detour to the fins. The fins were made out of 3/8 inch aircraft plywood as well. The scale demanded that the fins be 1.5 inches thick. So we took some ribs of maple and spaced them out on either side of the base fin, and then those were covered with a thin Lewin plywood, as you can see in this photo, and also epoxied and nailed onto the superstructure. It was amazingly strong, and this root edge that you're looking at where the hammer and glue is laying is what actually slid down into the rocket in slots cut in those lower base plates. Next we added fiberglass to those also and finished them off. This is the mold that we used for the cowling on the rockets. The cowling was the same on the stock fins as well as the oversized fins that we ended up using for the flight. We ended up building a set of flight fins that were 2 times upscale of the stock fins, just to ensure stability. You can't have a rocket weighing 1,600 pounds and have an unstable flight. So it proved out very well. It was a very stable flight. I detected no wobble at all in the flight. The fins themselves were 2X. The cowling stayed the same on either one. What we did is we laid 3 layers of fiberglass cloth into this mold, waited for it to cure, and then peeled it out. And as you can see in the next photo, here's the rough fin assembly, ready now for the ribbing and primer. This is one of the very interesting parts of the whole project. If you actually went around and counted on the rocket, there are about 1,000 wood ribs that were attached to the rocket to duplicate what the original Saturn V had on it. If you look at a Saturn V rocket, one thing you have to understand is NASA did not build a rocket and install fuel tanks into it. They basically stacked fuel tanks on top of each other, and where you see a ribbed section of the rocket is actually the structure that filled the area in between the fuel tanks and supported them. So anywhere that there's a rib on the rocket is an area between fuel tanks. That's why in the original Saturn V they had all the ice forming on the outside of it. It was from the liquid oxygen was actually right up to the outside edge of the rocket. But anyhow, different sections of rockets had different numbers of ribs. The sizes of the ribs were different. The taper on the ends of the ribs were different. And each one of these ribs, unfortunately, because they were so narrow, had to be drilled and nailed into place. So each one of these ribs is drilled, nailed, and epoxied onto the rocket. This portion of the build of the rocket took about 2 to 2.5 months between the detailing on the ribs and the fuel bypass tubes, the ullage motors. It's all a very time-consuming portion of the build. As you can see here, the fins on the original Saturn V were removable, and so they had to fit around the ribs. Those were actually bolted into place later in the build process of the Saturn V, but they had to cut each of these cowlings out to fit around the ribbing, and each one of them was different, unfortunately, due to the spans on the ribs. Here's a picture of casting one of the fuel bypass tubes. In the upper section, second stage, since the fuel tank went all the way to the outside of the rocket, they had to run the fuel lines around outside of the fuel tank so that the fuel didn't freeze, and these were actually the fuel feed lines for the J2 engines on the second stage. What you're looking at here is a duplication of the electrical conduits that run down the side of the Saturn V. The same problem here is the inside of the rocket was nothing but a solid fuel tank, so there were 2 electrical conduits that they ran all the wiring through so that the wiring did not have to go through the fuel tanks. Again, here we are in the ribbing process of the rocket. It's the center section of ribbing that I'm working on here has 234 ribs around the rocket, and trying to get the right size and the spacing on them correct so you ended up with the right number by the time you got around the rocket. I think I was within 2 ribs on each of the bands of having the correct number of ribs on the rocket. Here's the rocket ready for paint now. We've applied all the ribs. I built this rocket in 2 stages, basically. We built the bottom section, the 20-foot, which was actually been the first stage and second stage of the real Saturn V. I wanted to get it completed and painted up so that we could begin the process of getting vendors involved, getting sponsors involved. At this point in time, we got Rockets Magazine involved. So instead of trying to build the entire rocket and then paint it, we assembled the bottom section first, and in the next series of photos, you're going to see the painting process. Due to the size of the rocket, I had 2 friends of mine volunteered to help me paint it. And during the painting process, we had 2 guys, each with a spray gun on it, and I was turning the rocket. As you spray this paint, you have to keep the paint wet. And due to the size of the rocket, by the time one painter got around it, you'd have had dry spots in it. So we had 2 guys painting full time. We painted the white on a Saturday. About 8 hours worth of work to get the white on the rocket. We went in on the following day on a Sunday morning, and we taped the rocket up, which took about 2 to 3 hours, and we applied the black 2-tone to the rocket. And this was bringing the rocket home. I got a lot of neat stares from people. I don't think I created any accidents, but I actually hauled the rocket home on an open trailer. And I did get quite a few looks, a couple of swerved cars, and a lot of people breaking their necks trying to see what the heck I had on the back of my trailer. Now, since we had the bottom section painted, it was time to get the upper section constructed. As you can see here, this is the rough skeleton structure of the upper section. And you can also see the release arms on the transition section where it locked onto the bottom. These are the aluminum ribs that reinforce that joint where the separation device is located. There's a lot of stress with this thing hanging on the rocket, So we ran aluminum ribs in conjunction with the wood structure just to some added support to this area of the rocket. And the skinning process for this was basically the same as the skinning process on the bottom. We used 3.7 millimeter Lewin plywood. It got a little tricky on wrapping this upper section, but by the time I got it all done, I pretty much had it figured out, and it looked pretty decent. This is the covered upper structure getting ready for fiberglass. And here we are in the fiberglass process. After the fiberglass was put on, we took a grinder and roughed it back down and began to add the body filler to end up with a smooth finish on the outside of the rocket. After your body filler is done, of course, you go to a primer. And the same process here. We started adding ribs again. The ribs on the cowling, which was this tapered section you're looking at, unfortunately, the cowling was made out of fiberglass, and it was impossible to nail the ribs into place. So each one of those was glued with a real fast drying glue and held up pretty well. We only lost one or two of them actually in the flight. I painted the entire upper section myself in my garage, a little smaller, a little easier to handle. And we're two-toning the upper stages of the rocket, two-toning the fiberglass cowling for the transition section. My brother owns a graphics and embroidery business, and after a little arm twisting here and there, Brian cut out the letters and all the intricate detailing for the rocket, and he came over on a Sunday afternoon, and here we are applying the decals to the rocket. This is a shot of the build of the nose cone. Same basic structure here. It's the 3/8 inch plywood. Cut triangles for the correct taper on it. Filled the area between them with foam and fiberglass those in. The launch tower itself was a weekend of work with dowel rods and pins. We actually glued the dowel rods into place, and then after the glue had set, we drove dowel pins into each of the joints to try to reinforce them. You're looking here at the set of flight fins for the rocket. The original fins, the scale fins, weighed about 16 pounds apiece. When we were done with these, we'd increased the weight to about 27 pounds apiece. But it was kind of a necessary evil to stabilize the flight of the rocket. You're looking at the oversized version of the fins on the rocket now. The fin span across these at the base of the rocket was 9 feet. This was one of the things that really aided us in the pinpoint landing that we were able to achieve, as it had such a wide footprint and we had such calm winds for the flight that they ended up sitting up on them very well. And this is kind of a funny picture here, but I spent many hours doing just this during the build of the rocket. Standing there scratching my head going, how in the heck am I going to pull that off? But this was one of the areas we had, was the separation area. Now here's an area for some serious discussion. But this is the release mechanism that we used. As you remember earlier, the aluminum pins sticking out of the top of the bottom section. What you're looking at is the base of the what I call the transition section, where it tapers down from the 40-inch diameter to the 26 inches in diameter. And what I ended up doing, this was the early prototype, we made a wood wheel in the middle, and we had links coming out of the wood wheel out to a catch out toward the outer part of the perimeter. And as you rotate that wheel, it would release all 8 catches at the same time, which gave me an incredibly strong, secure lock when the mechanism was locked, but also provided a pretty much fail-safe release mechanism. Once you release those, it was going to fall off of the rocket if the airbag didn't blow. But what I achieved there was nothing that had to slide together or slide apart in flight. What we ended up doing for the release mechanism was a seatbelt pretensioner, as you're seeing here. This is also the earlier prototype before we added the aluminum wheel. But this is a device that is used in a lot of automobiles. When your airbag system, you get in an accident, your airbag system goes off, This device actually pulls your seatbelt tight before the airbag in the steering wheel goes off. I got a hold of about 20 of these, which allowed me for doing some testing. What we determined was that they had more than enough power to release all 8 catches in any condition. No matter how much stress, we weighted the tip of the rocket with about 200 pounds of weight, and it still released without a hitch. Now, there were 4 of these pretensioners all attached to the wheel. All of the altimeters and the radio control systems were attached individually to the pretensioners. We only needed one of these systems to work for the mechanism to release. Just in the name of redundancy, we had 4 separate pretensioners in there. Any one of them could release it. As soon as it sensed that the release had happened, then the airbag went off to push the upper section off. Early into construction, I realized with the amount of thrust that we were putting into this, I needed an extremely strong base plate for the rocket. And this plate is 1/2 inch thick. It is 7075 T6 aluminum. It's just an incredibly hard, dense aluminum. And FM Machine in Akron, Ohio here purchased the aluminum and did all the machine work on it for me for the Saturn V. They also machined all 8 retainers for the end motors. And as you can see, if you look closely, there's 4 nuts. Only 2 are visible in this picture, sticking out beside the motor casings. These were the attachment points for the steel cables that we attached the parachutes to. They ran the entire length of the rocket, mounted through that base plate, and they were 3/8 of an inch thick aircraft grade steel cable. I think the breaking tension on each of them was 15,000 pounds. So if we broke those cables, we were in trouble, but it's a very strong way to anchor it, come all the way back through the base plate. These were the guide rails, guided wheels for coming off of the launch tower. There was 3 of these on the rocket. These bolted into a steel structure inside the rocket. Also worked very well. We detected no catching on the rails. Here we're trying to determine our balance points. And unfortunately, we couldn't tie a string around this and swing it over your head like we used to do the Estes rockets of years ago. We actually had to hang the rocket. So I had dummy motors made up. I poured rocket tubing full of concrete. We duplicated the 380 pounds of weight of the rocket motors. We loaded chutes in it. We put the fins on it. You'll see 2 bags of wood pellets back there. That's because we were unable to put the bottom 2 fins on because it was sitting too close to the ground. But those 2 bags help compensate for the other 2 fins that we did not have on it. And we actually hung 1,650 pounds of rocket from the webbing you're seeing in the middle of the picture there. And what was amazing to me is the rocket didn't creak, groan, crackle, nothing. It was so incredibly strong, it surprised me. I kind of expected to see it bend and hear things cracking and popping, but none of the above. That structure just has turned out to be probably more than we needed, but we didn't have to worry anything about a structural failure. What we're looking at here is the very base of the nose cone. I used an airbag to push the bottom 2 sections apart, but we also used an airbag to pop the nose cone off of the rocket. And what you're looking at is simply the charge for the airbag is that black round unit in the middle of the bottom of the nose cone. Alongside each side of it was a backup charge. Each one of those held 15 grams of black powder. Should the airbag have failed, then those charges would have pushed the nose cone off. Or if you look in the top left corner of the picture, you're going to also see a quick coupler. Now when the airbag detonated and pushed the nose cone off, it also unplugged the coupler to those 2 black powder charges. I didn't want those black powder charges going off unless we absolutely had to do that. And the steel cable hanging down on both sides was actually the parachute attachment point.